Well, then let's get started. So I was telling you that this was one of my favorite classes to teach. And just to give a little bit of background, like I was the first person in my family to ever go to college, so I had no idea what major to be in. And I kind of got wind that if you were good at math and science, you should probably look into engineering. And so that's the way I did. I was born and raised in Maryland, and I jumped the border and I went to Virginia Tech for school. And I was there for 8.5 years. They couldn't get rid of me. They just ran out of degrees that they gave. Otherwise, I'd probably still be there. But I like Blacksburg. But I like Atlanta, too. And Virginia Tech is a little bit different than Georgia Tech because you don't have to declare your major as an engineer. Everybody is enrolled their first year in general engineering. And it's not until like late spring where you have to commit to a field. And we did it in this class called Engineering Fundamentals, where the instructor passed out a form and you wrote down what kind of engineer you wanted to be and you handed it up. And to be honest, like I had no idea what I wanted to, what kind of engineering. I didn't even know any engineers. I didn't know what any of them really did. So my roommate, my lottery roommate at Virginia Tech wanted to be an electrical engineer like his dad. And I said, oh yeah, Deepak, he's pretty cool. I'll be an electrical engineer too. And I remember too, I went on these open houses. Like that was one of our assignments before engineering fundamentals class. We're supposed to go and visit these little open houses that all the different engineering disciplines had to kind of recruit the students. I remember, like mechanical engineers, they had some lame thing about robots that didn't interest me, and the chemical engineers had a bunch of test tubes on the table, and that was kind of boring looking. But the electrical engineers, they gave me a tour of some of their labs, and one of this fiber optics lab, they actually gave me a fiber optic length. It was only like 20 centimeters long. They gave it as a souvenir, and I was like, oh, that is cool. So Double E was the only one that gave me anything, and therefore I decided to sign up for a Double E, and it kind of worked out. So. I commiserate you if you're making decisions in your life that are grossly uninformed at this point in your development. Sometimes it works out. So anyway, I got in the Double E curriculum, and the class that I got really excited about was electromagnetics. To give you a little bit of background, like I was kind of like this self-taught crackpot programmer. I never liked playing video games, but I loved like coding them. And I was liked graphics. This is like the early 90s when everything was two-dimensional. And I was just fascinated with graphics and high-speed rendering of environments and things like that. And I probably would have gone on to make millions if I had just stuck with that. But instead, I took electromagnetics class, and I suddenly realized that the math is the same. And the physics and the underlying how it works is very similar. In fact, there's a very tight connection between electromagnetism, not just the underlying math, and not just computer graphics in general, but art, how things look. As a hobby, part-time hobby, I'm actually an oil painter, and I like to do artistic things. And it's amazing how reinforcing it is. You'll find we're going to talk about a famous artist who also got sidetracked by electromagnetism in our lecture today that we start off with. And that's sort of how I came to kind of fall in love with the field of electromagnetism. And the thing you have to realize, a lot of people, I know, you don't want to be here because you're like, man, I just want to code, or I don't want to do anything with physics. But I hope that you see there's a lot of value, especially by the end of the course, in studying electromagnetic phenomenon. It's a very powerful discipline because it's really how you understand the technology of electrical engineering at its most foundational levels. If you can understand the E-fields of the devices that you're playing around with, everything else is a cakewalk after that. It's much easier to move up the protocol stack and build your understanding on that fundamental physics, as opposed to trying to do it the other way, which a lot of people try to do. They get into the business of technology and then expect to understand how it works and how to ask meaningful questions about technology from that background. That doesn't work. I think this is a really good class for stretching your conceptual ability. You know, I sometimes we've just went through this whole process of revising the curriculum, and it's an important discussion to have among faculty members. Although at the end of the day, no matter how good the curriculum is, you guys are going to forget 90% of what you've been taught, and then you'll go out in the world and do a whole bunch of things, some of them completely unrelated to electrical engineering. That no matter how well we tweak our curriculum, that's going to be true. It's really developing those kind of habits, both in your administration of your courses, as well as habits of the mind that I think you're really going to take away from you in Georgia Tech. And this class will stretch your conceptual abilities like none other. It's like going to the mind gym. When you start talking about three-dimensional fields that are themselves functions of three-dimensional space, and we will be solving those problems. So, buck up. You're about to go to the gym. I think there's a lot of creativity in our profession as well, in our little subdiscipline of electromagnetics. The art connection was maybe the first glimpse of that, and I hope you see that as we go along. And as I like to tell my grad students too, it's like, you know, if you're doing some EM theory, this is like some of the closest thing to magic you will see in the world, right? And think about it. We put these really bizarre symbols on the thing, and somehow that calls into understanding this alien technology of iPads and smartphones and displays and wireless communications and antennas and all the great technology that we kind of take for granted today. It really is kind of like magic, and sometimes when you've been studying it for a long time, you forget that, just how incredible it is. And then there's the art connection that I wanted to talk about. There's a guy named Samuel Morse. Samuel Morse, should say. And he lived from 1791 to 1872. And he was a very accomplished artist, especially in the early 1800s. He would do a lot of like U.S. government paintings where he'd come in and he'd paint the Senate and famous landmarks. And very accomplished, one of the most famous painters of his day. And there was a famous story involving Samuel Morse where in 1825, when he was called down to Washington to do a portrait, his wife, who I believe was at their home up in Connecticut, grew ill. And of course, back in those days, the only way to send messages were by horse courier. You bundle up a message and put it on a horseback rider and send it down to wherever. And it would take a long time. And so Samuel Morse is doing this painting down in D.C., and he receives this message that says, your wife is ill and is convalescing. And immediately he drops everything and goes back up to Connecticut. And it turns out that she had passed away already, and she was even in the ground already. So it was too late. And he was deeply brokenhearted by this. And so it sort of became a passion of his after that instant to increase the rate at which communications happened, because in the giant lag that it took that message to get to him in D.C., all these terrible personal tragedies unfolded. And so Samuel Morse embarked on this journey to try to increase the speed of messaging. And he eventually founded one of the first telegraph companies. He's kind of attributed as the inventor of the telegraph, although there were actually a lot of different people that were trying different telegraphing schemes at the time. His just happened to have the unique combination of being very cheap and effective, and figuring out how to implement technology without being too elaborate, which is, I think you'll find, a key to success as you get later in your engineering career. It's good to have new ideas. It's also good to figure out what's the simplest way to implement them. You don't get credit for complexity in the real world when you're doing your engineering. So let me show you what he was working on. The telegraph has a source and a switch at the sending end. And this area here this is called the key, to use old-time terminology. And what typically happens is that there's a ground here. And Samuel Morse's telegraph was a single-wire implementation. Now, in order to complete the circuit, you actually use the ground path. So electrically, we can model that as a conductive pathway, too. And then there would be some sort of load. It would either be a relay, which was a device that was used to amplify this pulse or switched signal that was sent down here, or it would be a register, which would be an inductive. In either case, it looked like kind of an inductor and a resistor. The register would be the electromagnet on the other end that would tap out the code depending on the signal that was traveling down. So this looks like a kind of a conventional circuit that you're used to seeing in your classes, in maybe your circuit theory class. But the only difference is that this length here is really long. You know, if this is good copper conductor, the only difference in the model that I've drawn up here is that, well, copper's a really nice conductor, but if you got a lot of it, like miles of it, the series resistance, even though it's very tiny, does tend to add up. So there's probably a little more resistance here on this path than this path that we could model if we wanted to. And it was actually Samuel Morse's unique kind of register implementation and relay implementation where he would have segments of telegraph wires that would amplify after you got to a certain relay. This is just a big electromagnetic that closes an external switch that allows more current to flow through a second path. So it was a kind of a way, what we would call a regenerative repeater in modern day engineering. You'll notice that the system is also digital, right? It's ironic that the first communication network, electrically speaking, was a digital network. It took us over a century to go full circle and come back to the digital world of things in the 50s. But, you know, relays, that was the only way to amplify signals. You didn't have vacuum tubes. You didn't have transistors back in this era. And they did understand some basic circuit theory back then. But they noticed these systems would behave very differently. When this system got very long, what you put in on one end was not necessarily what you got out on the other end. So in other words, you tap out something that looked kind of like a square wave. And then on the output here, sometimes you'd get some really weird kind of like ringing effects. If it got too bad, maybe your register wouldn't even tap out a nice square wave in response to the input on the other side. What was going on there? Well, it turned out that people had been using, like you're all accustomed to using in your linear circuits class, what we like to call linear lumped sum or lumped element, I should say, lumped element circuit theory. This is where everything in the world can be modeled by capacitors, inductors, resistors, and objects, no matter how complicated they are in the real world, always reduce down to something like this, or this, or this, or this. So it doesn't matter whether it's a giant piece of carbon, or if it's a little packaged resistor that you get out of the lab, or if it's a human body. It all looks like 20 ohms. And we represent it by a single discrete lumped element in your circuit model. And these don't really take into account they're in a way a higher level abstraction of what's really going on in the electromagnetic world. Right? Voltages and currents are kind of like one level above in abstraction to the E fields and the H fields that we'll be dealing with in this class. Now, we won't be dealing with them too severely until maybe 3 or 4 weeks from now. We're going to start off with transmission line theory, which kind of is a nice halfway house between circuit theory and field theory. So what happens is that if we go back to our transmission line with Samuel Morse, his telegraph line, it takes a physical non-zero amount of time for signals to travel. And what is a signal? A signal is really just the movement of electrons and charges, right? You know, when you have a voltage that's traveling down that transmission line, that's really an accumulation of charge separation between the ground and that wire. And that sort of represents the leading edge of your signal, the voltage waveform that's traveling down there. And we know intuitively from your physics class that nothing can travel faster than the speed of light, so it's not an instantaneous phenomenon. This is information traveling down on charges on your line. And there is a finite amount of time that has to elapse before you see anything on the other end. And that causes some problems. That's the main culprit for the ringing phenomenon that I sketched there on the board. That's what we'll be basically studying in the first, 3 or 4 weeks of the class. Now, you may want to say, you may want to ask at least, why do we study this type of system? This is an archaic technology. Nobody telegraphs anymore. But the key thing to recognize is that everything in electromagnetics scales with wavelength. This is one of the most important EE equations you'll ever learn. And this is just a basic equation from physics. Wavelength, which is usually measured in SI units of meters, times frequency, f, is equal to the velocity of propagation of a traveling wave. Units of meters per second. And this is a fundamental and really almost a mathematical result. If you have a sine wave in space and it is traveling in a direction, then it turns out that the wavelength is, if you were to freeze it in time, look at this particular node, which I've drawn as sort of a sine wave, a sinusoid with phase of 0, sine of 0 degrees, where we've got a node. If you add lambda distance in space, you should get back to that same node. That's how you define a wavelength. And so you have a frequency harmonic here. The wavelength is lambda. If the frequency is f, then the multiplication, the product of those two, is always the velocity of propagation. So everything scales with frequency in electromagnetics. And so let me do a little analogy here. With some numbers. If I want to send a good Morse code signal, the code named after Samuel Morse, you're physically tapping that out. So you're talking about a square wave that maybe has frequency content of like several hertz in its fundamental component. From your 2025 class, if you want to capture those sharp edges, you got to go pretty high in frequency. There's the sharp edges kind of ring at very high frequencies. And so let's just say that this is a 100 hertz signal to capture the good shape of this waveform. And you'd notice problems when you would transmit up to, say, 10 kilometers, 10 to the fourth meters. So we have distance, and here we have frequency. Well, now compare that to, say, a modern processor, where you are traveling at a frequency, you are sending signals down buses, and even within the chip, from core to core, at a frequency of 10 gigahertz. What is the analogous distance that corresponds to that if everything scales with respect to frequency? Well, if you change the same order of magnitude, you get 0.1 millimeters. That's one of the amazing things. Sending an electrical signal in the gigahertz regime when a motherboard or any circuit trace that's just a few inches is literally, electromagnetically speaking, almost like sending a Morse code signal across the country. And so what they learned on this old archaic piece of technology turns out to be really, really helpful to those of us who are working in the areas of high-speed logic and digital interconnects. And that's really the application that the next couple weeks of class will cover. What happens in those high-speed digital interconnects, and how do we analyze it? Now, for this thing over here, we're not going to draw, when we need to use transmission line theory, we're not going to draw just two lines like this. We actually have, I'm going to introduce to you today, a new circuit element that you can now put in your diagrams. And the one that I use, there's actually a couple different ways to represent this, but the one that I use, so saying we had a source, voltage as a function of time, the one I use is just 2 bars. So whenever you see 2 bars, think, that's a transmission line. Now, to specify, it's just like a regular circuit element. There are some parameters that I also need to specify to complete my circuit. You know, when I put a capacitor in there, I got to tell you how many farads is that capacitor. When there's a transmission line in there, I've got to tell you what is the intrinsic impedance. And that usually gets the variable Z0. And I should also tell you the distance. And I would be really doing you a favor if I told you the velocity of propagation. So you can relate frequency content to wavelength. And the reason why that formula is really nice, wavelength times frequency equals the velocity of propagation, is that it can clue you in whether or not you even need to use transmission line theory. For example, if I give you the velocity of propagation on a line, and I tell you, I am transmitting power from a substation in Alpharetta to downtown Atlanta, do I need to worry about transmission line theory? Well, as a rule of thumb, I tell students, roughly if the device that you're transporting electrical signals across is starting to be larger than 1/10 of a wavelength, then you start worrying about transmission line theory. If not, then you can go back, replace this with straight lines or little resistors, and use your classical lumped element circuit theory. But if you do get more than 1/10 of a wavelength in geometrical dimension, then you're going to have to start modeling with the theory that we're going to outline over the next couple weeks and start to look at things like reflections and transit times and that sort of thing. And in order to do that, you need this velocity of propagation, which you'd find in the case of going from Alpharetta to downtown Atlanta, you're talking like at 60 hertz, that's such a low frequency, and the wavelength is so large, you probably don't have to worry about it. They do tend to be very picky in the power industry. Even when the transmission line approaches, say, 1/100th of a wavelength, they tend to pay attention to transmission line theory and look at things like load transformation effects and that sort of thing. And that's because they're dealing with megawatts of power transmit. You know, they don't have as much tolerance as the average motherboard designer, for example, in percent error of their signals. So these rules of thumb are always kind of contextual, right? Depending on your application, you can get a much more tighter rule of thumb than just 1/10 of a wavelength. But that's a general rule of thumb. And you say, oh, well, what about, do I need transmission line theory if I need to study the cellular phone signals going from my base station shed on the ground up 60 feet to the antenna? You ever seen a cell tower like that? You got some antennas up there, and there's a coaxial cable that comes down into the base station. Are transmission line effects important there? Well, let's work through our little exercise. If we take the speed of light, 3 times 10 to the 8th meters per second, as sort of the upper bound of our the signals that could travel on a transmission line. Generally, they're anywhere from a half to much smaller than that, depending on how they're constructed. But for the most part, that's a nice upper bound. There, the wavelength for cellular frequencies, 900 megahertz, is about 1 foot. So that cable that leads up to there is actually tens or even 100 wavelengths long. So it becomes very important to model with transmission line theory. And so that's an example of the kind of rule of thumb calculation you'll be asked to do. I think you'll probably have a question on your homework to say, oh, which of these scenarios is a transmission line theory even important? Do we even need to bother with it? Now, one more point about this. I draw it like 2 bars here. Sometimes in your book, if you have like some fancy editor, you'll see like the 2 bars drawn like this. Oh, nice. You know, like they're 3-dimensional round bars. That's always nice. Sometimes you will see them drawn like this. They'll take this bottom bar away and they'll hook a source to it, and then they'll just leave a ground on that end, and they'll hook a load over here, and they'll put a ground here. Of course, these are electrically connected, so there's kind of an implied path to complete the circuit. It is a different way of thinking, though. One of the biggest problems that students have when they see the transmission line theory section is that we will be studying voltages and currents that move as a waveform down this structure, whereas most of you are thinking in terms of current loops, right? You're not used to looking at that kind of transient analysis. You'll get comfortable with it quickly, but just be aware that there's going to be some difference in what you've been dealing with in your elementary circuits class.